All right, so we're going to be talking about section 3, the integral and comparison tests here. Actually, the integral test, we already covered that in the lab. So, did it. And p-series, we also did in the lab. So we're more or less going to skip those two because we've already covered them, although I will review p-series real quick. One of the things we're going to be talking about sort of in the near future is we really want to figure out if a series converges or diverges. It's great if it converges if you can tell what it converges to, but sometimes that's really difficult. So we're also going to look at some methods of estimating the sum of a series. So first, let me remind you about the p-series. So the p-series we covered in the lab, and hopefully what you discovered as you went through that process is that the p-series, when you use the integral test to compare to this, you find that a p-series is convergent if p is greater than 1 and divergent if p is less than or equal to 1. Notice that the p-series test doesn't tell you what it converges to, it just tells you if it's convergent or divergent. And this should sort of make sense because if p is greater than 1, if you're getting something like 1 over n to the 7th, your denominator is increasing really quickly. So you're not adding a very large amount, which is why it would converge. So anyways, let's go ahead and use the p-series test to figure out whether these two series converge or diverge. So go ahead and do exercise 1 on your own. There's an A and a B, and there's also a C. The A and the B should be very straightforward and come straight from this theorem. C, maybe not so much. So go ahead and pause the video now. Try to do exercise 1A, B, and C. Okay, so this looks exactly like a p-series with p equal to 5, which last time I checked is greater than 1, so it converges. And why does it converge? Because it's a p-series. So I would write p-series with p equal to 5, which is greater than 1. B doesn't look exactly like our p-series, but we can rewrite it as the sum from 1 to infinity of 1 over n to the 1/3 power, which is a p-series with p equal to 1/3, which last time I checked is less than 1. So this thing diverges. All right, letter C. Here, the idea of this one, how we can connect it to a p-series, so we can kind of say, well, look, the biggest term here is n. Like, as I go to infinity, that n is going to become the biggest thing in the numerator. And as I go to infinity, that n cubed is going to be the biggest thing in our denominator. So this is like doing the sum of n over n cubed, which is the same thing as 1 over n squared, which converges. It's a p-series with p equal to 2, which last time I checked is greater than 1. Now I can actually make this completely mathematically legitimate, and here's how I'm going to do it. If I was going to sum from n equals 1 to infinity, n minus 4, over n cubed plus 2n squared plus n. Suppose I wanted to make that look a little bit nicer. Well, I could remove the minus 4 from the top. Now, if I'm taking off 4 from, or sorry, if I'm really what I'm doing there is I'm increasing my numerator by 4. So if I'm increasing the numerator, then this thing here has to be bigger. That summation is going to be bigger than what I started off with. Because every time that I'm doing a minus 4 over here, that makes it smaller. So if I remove that minus 4, I'm going to get an expression that's a little bit bigger. And similarly, what if I took away the 2n squared plus n from the denominator? Well, if I take those away, I'm making the denominator a little bit smaller. And if I make my denominator smaller, I'm going to make my overall expression bigger. And I should really make this look a little bit nicer. So, and just if you wanted to just think about this, like suppose I plugged in, I don't know, n equals 1. Here I would be getting a negative 3 over 1 plus 2 plus 1 is 4. And here I would be getting a 1 over 1. 1 over 1 is definitely bigger than negative 3 over 4. Because I've increased the numerator by 4, and I've made the denominator smaller. Well, what do I notice about this? This is the same thing as what I had up here. Here I said it was like that. Here I actually made that more explicit and say my original series is actually going to be less than that. Less than that 1 over n squared. And this converges. So if I'm less than something that converges, then my original thing converges as well. And there's actually a formal way of doing this. It's called the comparison test. So here it says you have to be given two sums with series with positive terms. They don't actually have to all be positive terms. They just have to eventually be positive terms. So you notice like in this one, n minus 4 started out as with some negative terms, but then eventually they became positive and they were all positive. So what the comparison test says is that if you have two series, A and B, if the B converges, and it happens to be true that all of your terms for the B series are bigger than the A series, then your A series converges as well, right? And this is a lot like we've talked about before with comparison theorems and the squeeze theorem and stuff like that. If you have something that's bigger than something else, and we know that the bigger thing converges, then the bottom thing is going to converge as well. Similarly, if the B series diverges, and we happen to know that the A series is always greater than or equal to the B series, if the smaller one diverges, then the bigger one, in this case the A, also diverges. So let's do an example of how we can use this. So the question is, does the series 1 plus sine n over 10 to the n converge or diverge? And the issue here is that the sine function kind of bounces all over the place. So it's kind of annoying, but it bounces really just between 1 and negative 1. So I'm going to do some rough work over here. I'm going to say, well, look, if I'm doing the sine of n, that's always going to be in between 1 and negative 1. Now on the top of this here, I don't just have sine, I've got 1 plus sine. So let's add 1 to everything. When I add 1 to everything, I get 0 is less than or equal to sine of n plus 1, which is less than or equal to 2. So now I can go back to my originally scheduled series, and I can say that this 1 plus sine n over 10 to the n, that's always going to be less than or equal to 2 over 10 to the n, right? Because I've got here my sine of n plus 1 is less than or equal to 2, and then all I did was divide both of those things by 10 to the n. And now I can put my series in front of it, right? If each of those terms is less than or equal to it, then the series is also going to be less than or equal to it. And what do I notice about this? Well, I can factor that 2 out. And I can also, that 1 on top, I can put inside parentheses and write it like this. And this is a geometric series. So it's geometric with, what is it, my ratio r equals 1 over 10, which is less than 1. So it converges. And here we could actually calculate what this converges to, but it turns out that that isn't going to be useful for us, because I know that I can tell you what the top thing converges to, but I still wouldn't know what my actual series that I'm interested in is going to converge to. I just know that it's going to be less than that. So this part is geometric. If it converges to a certain something and then I multiply that by 2, it still converges. So this means that the sum 2 over 10 to the n converges. And then by the limit comparison theorem, or the, the comparison test, this means that 1 plus sine of n over 10 to the n converges as well. The end.